1,000 light-years sounds like a distance, but for a human traveler, it quickly becomes a problem of time. At the speeds of the spacecraft we know how to build today, the journey would last for millions of years. While making it short enough to fit inside a human life would require moving so close to the speed of light that the voyage itself begins to change. As speed rises, dust that seems harmless becomes a serious threat. Radiation becomes harder to shield against. The sky begins to change, and the people you left behind may age far faster than you do. So tonight, the question is simple. If a human being somehow traveled 1,000 light-years through space, what would actually happen along the way? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you could choose any destination exactly 1,000 light-years from Earth, what would you hope to find there? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about what would actually happen if you traveled 1,000 light-years. 1,000 light-years is easy to say, because it sounds like a single number. But the moment we try to turn that distance into a real journey, the scale changes completely. Light itself needs 1,000 years to cross it, and nothing with mass can move as fast as light, which means every spacecraft we could actually build would need longer. The distance is not just large in the ordinary sense, it is large enough that time becomes part of the destination. To see how extreme that is, it helps to begin with the fastest objects humanity has already sent away from the Sun. Voyager 1 is moving through interstellar space at a speed that seems enormous by everyday standards, crossing billions of kilometers each year, yet at that rate, a journey of 1,000 light-years would take on the order of tens of millions of years. A spacecraft could leave Earth while humans still existed in our present form, and arrive after entire species had appeared and vanished. Continents had shifted, and the surface of the planet had been remade many times. That is the first uncomfortable truth about interstellar travel. Speeds that feel extraordinary inside the solar system become almost meaningless once the distance between stars is allowed to grow. A mission to Mars can be measured in months, a journey to the outer planets in years. But 1,000 light-years belongs to a different category altogether. The spacecraft is no longer simply far from home. It is separated from home by a duration so large that ordinary human planning stops making sense. Even if the ship could travel 10 times faster than Voyager, the voyage would still last far longer than recorded history. At 100 times Voyager's speed, it would remain a journey measured in hundreds of thousands of years. The problem does not disappear through modest improvements. Because 1,000 light-years is too large for incremental progress to make it feel human. To bring the journey down into centuries or decades, the spacecraft has to enter an entirely different speed regime. This is where the title begins turning from a question about distance into a question about physics. We are not asking how long a rocket engine can run or how much fuel a conventional spacecraft can carry. We are asking what happens when a human-made vehicle tries to move fast enough that 1,000 light-years no longer requires millions of years. The answer pushes us toward fractions of the speed of light, where every increase in velocity becomes harder, more expensive, and stranger. At 1% of light speed, the spacecraft would already be moving at roughly 3,000 kilometers every second. That is far beyond any crewed vehicle humanity has ever operated. Yet the crossing would still take around 100,000 years if we ignore acceleration and braking. A person stepping aboard such a ship would not be starting a voyage they could finish. They would be entering a project designed for civilizations, generations, or machines. At 10% of light speed, the situation changes dramatically, but not enough. The ship would cross the distance in roughly 10,000 years from Earth's frame, still far beyond any ordinary human lifetime. A vessel capable of surviving such an interval would need to preserve not just people, but an entire functioning society. or else remain autonomous for longer than nearly every human institution has ever existed. The speed sounds futuristic, but the journey remains ancient in scale. Half the speed of light begins to make the number feel smaller. Ignoring acceleration and deceleration, 1,000 light-years would take about 2,000 years, as measured from Earth. That is an astonishing improvement compared with Voyager, but the people who watched the launch would still belong to remote history by the time the spacecraft arrived. The civilization receiving news of the mission would almost certainly not be the civilization that sent it. The idea of a destination also becomes more complicated, because the target cannot be treated as a fixed point. Stars move through the galaxy, and over thousands or tens of thousands of years, their positions change significantly. If a spacecraft were aimed at a star 1,000 light-years away, engineers could not simply point at where the star appears today. They would have to predict where it will be when the ship arrives and aim for that future position instead. This means the journey is already a problem in both space and time before the spacecraft even leaves. The target has a present location, a visible location delayed by the time its light takes to reach us, and a future location that matters to the ship. A star, 1,000 light-years away, is seen as it was 1,000 years ago, while the spacecraft has to arrive where that star will be thousands of years from now, depending on the speed of the journey. Even choosing a destination becomes strange when viewed this way. The star we observe through a telescope is not the star as it exists today. It is a picture carried to us by light that began traveling centuries ago. A ship sent toward it would leave based on measurements of an object whose visible image is already old. Then, spend centuries or millennia moving toward a future version of that system that no one on Earth has ever seen directly. The distance, therefore, creates a delay in knowledge before it creates a delay in travel. We are always looking into the past when we look at the stars, but 1,000 light-years makes that delay large enough to feel historical. If a civilization existed around a destination star and built a bright structure today, Earth would not see it for another 1,000 years. If the structure vanished tomorrow, the old image would continue traveling through space long after the event itself was over. A traveler heading toward that system would be moving through the same stream of delayed information. As the ship gets closer, the light reaching it from the destination becomes more recent, so the travelers would gradually see the system's history unfold faster than observers on Earth. The closer they move, the less outdated the image becomes, until arrival finally places them in the same local present as the star they have been watching from afar. Behind the spacecraft, the opposite happens with Earth. Light, leaving our planet, continues chasing the ship outward, carrying images of the world the travelers left behind. Depending on the ship's speed, those images may continue arriving for years or centuries, allowing the crew to look backward and see a delayed version of home. The farther away they travel, the more disconnected those images become from whatever is actually happening on Earth at that moment. At relatively low speeds, the ship would simply age along with the rest of the universe, and the problem would remain brutally straightforward. A 10,000-year journey takes 10,000 years for the travelers as well, which means no individual human can complete it. The only possible solutions would involve generation ships, suspended animation, radical life extension, or fully robotic travel, each of which creates a different kind of mission from the one suggested by simply imagining a person sitting inside a fast spacecraft. A generation ship would turn the distance into a moving world rather than a normal vehicle. People would be born, live, and die inside it without ever seeing Earth or the destination, while their descendants inherit a journey they did not choose to begin. The spacecraft would need to recycle air, water, food, materials, and knowledge for thousands of years. And every system failure would matter because there would be no rescue mission capable of reaching them quickly. Suspended animation sounds simpler, but it remains speculative at the scale required for human beings, especially across centuries or millennia. Even if biological aging could be slowed dramatically, the ship itself would still experience every year of the voyage. Machines, seals, electronics, structural materials, and shielding would continue aging while the passengers slept, so the problem of time would simply move from the human body into the spacecraft. Robotic travel avoids some of these difficulties because machines do not need food, air, or psychological stability. But 1,000 light-years still creates an enormous communication delay. A probe arriving at the destination could send a message back immediately, and Earth would wait another 1,000 years to receive it. By the time the answer arrived, 2,000 years would have passed since the original departure, even if the outbound trip somehow took almost no time at all. This is one of the reasons interstellar distance feels fundamentally different from travel on Earth. On our planet, communication is usually much faster than transportation, so a traveler can remain connected to home while moving. Across 1,000 light-years, communication itself becomes part of the isolation because no signal can outrun light. The spacecraft can move faster, the engines can improve, and the crew can survive longer, but no technology can make a message cross the distance instantly. The journey therefore separates people in two ways at once. There is the physical gap between the ship and Earth, and there is the growing delay between events in one place and knowledge of those events in the other. A message sent from Earth when the ship is 500 light-years away needs 500 years to reach it, and any reply requires another 500 years to return. Conversation becomes impossible in the ordinary sense because each exchange belongs to a different historical era. If the travelers need help, the problem becomes even more serious. A failure discovered hundreds of light-years from Earth cannot be discussed in real time with engineers at home. Even if Earth sends perfect instructions the moment it receives the message, the solution may arrive centuries later. The crew has to carry the ability to diagnose, repair, redesign, and manufacture what it needs, without depending on people who are separated from them by centuries of light travel. At this point, the simple idea of traveling 1,000 light-years begins to reveal what it really demands. The distance is not just something the engines have to cross. The spacecraft has to survive the time created by that distance. The crew has to live through it. The target has to be predicted into the future. And communication with Earth has to endure delays so long that the word communication almost stops applying. The only known way to make the experience dramatically shorter for the traveler is to move much closer to the speed of light. Once the spacecraft enters that regime, special relativity begins changing how much time passes aboard the ship compared with Earth. The journey can still take more than 1,000 years from Earth's perspective, yet the travelers themselves may experience far less. This is the point where the story stops being purely about building a faster engine and begins becoming about changing the relationship between distance and time. The spacecraft does not make the 1,000 light-years disappear, and light still sets the ultimate speed limit. But the travelers can experience the crossing differently from the people who remain behind. That possibility is what makes extremely high speed so tempting. A voyage that would take thousands of years at ordinary interstellar speeds can, in principle, be compressed into a much shorter span for the crew, if the ship moves close enough to light speed. The price is that every part of the journey becomes more difficult. The energy rises enormously. Collisions become more dangerous. Radiation changes, and the separation in time between the travelers and Earth becomes much greater. So the first real challenge is not choosing what star lies 1,000 light-years away, but finding a speed that allows a human being to reach it before their own lifetime ends. Once that requirement is added, almost every comfortable assumption about spacecraft design disappears. Because the ship has to move through space at velocities where even emptiness begins behaving differently. and to understand what a 1,000-light-year journey would actually do to the people aboard, the spacecraft itself, and the world they leave behind. The next question is, how close to the speed of light a human ship would have to travel before the voyage could fit inside a human life? The answer begins with a limit that cannot be negotiated away by better engineering. Light travels through empty space at about 300,000 kilometers per second, and according to special relativity, an object with mass cannot simply be accelerated through that boundary. No matter how powerful the engines become, the spacecraft can only approach the speed of light more closely, never reach it in the ordinary way, which means the shortest possible travel time measured from Earth can never fall below roughly 1,000 years for a destination 1,000 light-years away. That fact immediately changes what fast enough means. From Earth's point of view, there is no version of this journey in which the ship leaves today and arrives a few decades later, because even a spacecraft moving almost as fast as light still needs just over 1,000 years to cross the distance. The only reason a human traveler could ever experience a shorter journey is that time itself does not pass at the same rate for a ship moving extremely fast relative to Earth. Before reaching that strange regime, however, the numbers remain stubbornly ordinary. At 10% of light speed, the ship would need about 10,000 years to cover the distance if we temporarily ignore acceleration and braking. At half the speed of light, the crossing falls to about 2,000 years. At 90%, the time measured from Earth drops to a little over 1,100 years, which sounds close to the theoretical minimum, until we remember that 11 centuries are still far beyond a normal human lifetime. The important change comes only when the spacecraft begins moving so close to light speed that adding another 9 to the number becomes more meaningful than doubling the speed. At 99% of light speed, Earth would measure a journey of a little more than 1,010 years. At 99.9%, the number falls only slightly further, to just over 1,001 years. From Earth's frame, pushing the spacecraft harder seems to produce less and less improvement, because the ship is approaching a speed it cannot cross. Inside the spacecraft, the story is very different. Special relativity allows the travelers to experience less time than observers who remain on Earth, and the effect grows rapidly as the ship approaches light speed. At 90% of light speed, the reduction is noticeable, but not enough to make the voyage human, while at 99%, it becomes much stronger. Around 99.9%, an idealized 1,000-light-year cruise could take only a few decades of traveler time, even though more than 1,000 years pass on Earth. This does not mean the ship somehow cheats its way across space faster than light. Earth still measures the spacecraft moving below the universal speed limit, and a beam of light sent toward the same destination would arrive before it. What changes is the amount of time measured by the travelers themselves, because motion at relativistic speed changes the relationship between space and time. The 1,000 light-years remain real, but the crew does not experience the same duration that people on Earth do. That is the first point, where an individual human journey begins to appear possible in principle, although the word possible is carrying an enormous amount of weight. A ship moving at 99.9% of light speed would be operating in a regime far beyond any vehicle humanity has built. And reaching that velocity would require far more than simply attaching a larger engine. The spacecraft would need to accelerate for a significant period, protect its crew during that acceleration, carry or receive an extraordinary amount of energy, and later remove almost all of the same speed before arriving. Acceleration matters because a human crew cannot instantly jump from rest to relativistic velocity. An immediate change to 99.9% of light speed would destroy any ordinary structure and every person inside it, so the increase has to occur gradually. If the ship accelerated at roughly the same strength as Earth's gravity, the crew could experience something close to normal body weight, while the spacecraft steadily gained speed, turning the floor toward the rear of the ship into an artificial down direction. At that comfortable acceleration, reaching extremely high fractions of light speed could take years of traveler time rather than seconds, and the distance covered during the acceleration would become significant. The ship would then need a corresponding period of deceleration near the destination, because arriving at almost the speed of light without the ability to slow down would turn the mission into a flyby lasting only a brief moment. A real journey has to include both the effort required to gain velocity and the equally difficult problem of losing it. This creates a more subtle picture than simply choosing a cruising speed from a chart. The fastest part of the journey may occur only after years of acceleration, while the final years aboard the ship are spent slowing down again. If the acceleration is gentle enough for humans to tolerate continuously, the crew could experience something close to ordinary gravity during those phases. But the ship itself would be operating under thrust for an extraordinarily long time compared with any propulsion system used today. A hypothetical journey using constant, comfortable acceleration for roughly half the distance and constant deceleration for the other half produces one of the strangest results in the entire idea. From Earth's perspective, the voyage still takes a little more than 1,000 years, because the spacecraft can never outrun light. For the travelers, however, relativity could reduce the experience duration to only around a decade and a half, depending on the exact acceleration profile. The ship would reach a speed so close to light speed near the middle that the difference is almost impossible to express intuitively. This kind of calculation is useful because it shows that the physics itself does not forbid a human from experiencing a 1,000 light-year crossing within one lifetime. The barrier moves somewhere else. Instead of time being the obvious impossibility, energy, propulsion, shielding, navigation, and survival become the problems that dominate the journey. Relativity offers a path around the lifetime problem, but it does not offer a practical machine capable of following that path. The energy requirement grows sharply as velocity approaches the speed of light. A spacecraft cannot be treated like a car, where twice the fuel simply produces twice the speed, because relativistic motion changes how energy and momentum behave. Each additional increase near light speed demands more energy than the one before it, and reaching the exact speed of light would require an unlimited amount for any object with mass. The final fraction becomes harder, precisely when the time dilation becomes most useful. This creates an uncomfortable trade. If the ship travels slowly enough that the energy demands remain remotely recognizable, the crew cannot personally survive the duration without some other solution to aging. If the ship travels fast enough for relativity to compress the voyage into one lifetime, the propulsion challenge becomes enormous. There is no comfortable middle speed, where both problems quietly disappear. Mass makes everything worse, because the engines are not accelerating only the people aboard. The ship needs a pressure vessel, radiation shielding, life support equipment, power systems, repair tools, computers, food production or storage, and whatever propulsion hardware is required to maintain the journey. Every kilogram added for protection must also be accelerated, which requires more energy, and any additional propulsion hardware adds more mass of its own. A very small, robotic probe is difficult enough to imagine at a significant fraction of light speed. But a human spacecraft would be far heavier, because people cannot be reduced to a camera and a transmitter. The crew needs a habitable environment for years or decades of experience time, and the vehicle has to remain functional, with no possibility of repair teams arriving from Earth. The result would likely be one of the most complicated machines ever attempted, yet it would have to be pushed to a speed where even a tiny design weakness could become catastrophic. As the ship gained speed, those familiar conditions would disappear, one by one. Communication delays would become weeks, then months, then years, while the planets become impossible to distinguish with unaided vision. The Sun would slowly change from the star that dominates the spacecraft's environment into one point among the surrounding stellar field, and the crew's sense of where home is would depend increasingly on instruments rather than on anything they could see directly. The acceleration itself would also reshape the route. A ship traveling at relativistic speed cannot casually turn around like an aircraft, because change in direction means changing an enormous amount of momentum. Course corrections have to be planned carefully, and even a small error in direction can grow into a large miss after hundreds of light years. The faster the craft moves, the more important it becomes to know exactly where the destination will be, centuries later, in Earth's frame. This makes navigation a problem of prediction, rather than simple steering. The target star is moving, the spacecraft is moving, and the light used to observe the target is already old when it reaches the ship. A destination 1,000 light-years from Earth must be treated as a future meeting point, not as a bright dot the pilot can keep centered in a window. At extreme speed, even deciding when to begin slowing down becomes part of the same calculation. The ship cannot arrive near the target and then discover that the braking system needs several light-years to remove its velocity. A long deceleration has to begin well before arrival, which means the trajectory must be accurate enough that the spacecraft is already committed to the correct future position of the destination, while it is still separated from it by distances larger than the entire solar system. Only the external universe would reveal how unusual the motion has become, and even that view would not remain familiar. Light arriving from different directions would be altered by the spacecraft's velocity. Stars would appear redistributed across the sky, and radiation that seems harmless at rest could be shifted into more dangerous forms from the ship's perspective. The faster the crew travels, the less the surrounding universe behaves like the calm star field they left behind. Those effects matter, because the same speed that solves the lifetime problem creates the dangers that dominate the rest of the voyage. Interstellar space contains thin gas and microscopic dust, and at ordinary spacecraft, speeds those particles are mostly a minor engineering concern. Mere light speed, the relative energy of an impact rises dramatically, turning particles too small to see into threats the ship cannot simply ignore. The route therefore reaches an uncomfortable threshold. Below relativistic speed, the distance is too large for one person to cross. Near relativistic speed, the traveler's clock finally makes the journey conceivable, but the environment ahead begins becoming hostile precisely because the ship is moving fast enough to make the journey useful. Before those hazards appear, however, there is a quieter change that happens much closer to home. The ship has to leave the planetary system that gave every human journey its original reference point. And as acceleration carries it outward, the Sun, Earth, and the familiar arrangement of the planets begin shrinking behind it in a way no human traveler has ever experienced. And once the speed becomes high enough to make a human journey possible, in principle, the most immediate change is not in the clock or the engine, but in the view behind the ship, as the solar system begins shrinking into a single point of light. At the beginning, leaving Earth would still feel connected to ordinary space travel. The planet would grow smaller behind the spacecraft, the moon would become harder to separate from it, and the sun would remain overwhelmingly bright compared with every other star. Even after crossing the orbits of the outer planets, the crew would still know exactly where home was, because the solar system would dominate their sense of direction. The distances would be enormous by human standards, but they would still belong to a place whose structure is familiar. That familiarity would not last very long on a 1,000-light-year journey. Once the ship travels beyond the planetary region and continues accelerating outward, the individual worlds disappear from unaided view. Jupiter, Saturn, Earth, and the rest would no longer be visible as separate objects, while the Sun would slowly lose the special appearance it has from within its own system. It would remain a bright star for a while, but each additional light year would make it less distinct from the stellar background. The change would be gradual rather than dramatic. There is no border in space where the solar system suddenly vanishes behind the ship, and no moment when a warning light announces that home has become too far away to see. The planets simply fade from view, while the sun becomes smaller and dimmer. From a few light years away, the sun would already look like an ordinary point of light, rather than the disk that filled the sky near Earth. With sufficiently powerful instruments, the crew could still identify it easily, because they would know exactly where to look and how it should move relative to nearby stars. To human eyes, however, the emotional difference would be enormous. The object that once lit every day of their lives would no longer look fundamentally different from other stars. Earth would disappear much sooner. The planet is tiny compared with the sun, and shines mainly by reflecting sunlight, so seeing it directly across interstellar distances would require sensitive instruments and careful observation. The crew could still know where Earth was in a mathematical sense, but knowing a coordinate is not the same as seeing a world. Long before the spacecraft has traveled even a small fraction of the full distance, the planet that launched the mission would have become invisible without technology. That creates a strange kind of separation, because almost everything the crew remembers about home would still exist in their minds with complete detail. They would remember roads, weather, rooms, faces, oceans, and the ordinary scale of life on Earth. Yet physically, all of it would occupy a point too small and faint to distinguish. The entire human world would be compressed into a direction behind the spacecraft. Communication would keep that connection alive for a time, although every message would arrive later than the one before it. 1 light year away, a signal from Earth needs 1 year to reach the ship. 10 light years away, the delay becomes 10 years in one direction. At 100 light years, a simple reply can no longer return within the lifetime of many of the people who sent the original message. Early in the voyage, people on Earth might still send mission updates, personal messages, scientific data, or changes in navigation plans. The crew could receive them days or months later, and the delay would be inconvenient without being emotionally impossible. Farther out, a message might arrive years after it was recorded, carrying voices from people who have already changed significantly by the time the crew hears them. At relativistic speed, the situation becomes stranger because the ship is not merely far away, it is also moving rapidly away from the incoming signals. Light from Earth can still catch the spacecraft, but the crew's motion changes how often successive waves arrive. Signals from behind would be shifted toward lower frequencies and stretched in time from the traveler's point of view, making the flow of information from home seem increasingly slowed and redshifted as their speed rises. A video message sent from Earth would therefore not behave like an ordinary live broadcast, simply delayed by distance. Depending on the spacecraft's velocity, the crew could receive information at a different apparent rate, with the sequence of events from home arriving stretched, compared with the way those events unfolded on Earth. Technology could correct the frequency shift and reconstruct the information, but it could not restore immediacy. The message would still describe a world whose present state lies beyond the crew's direct knowledge. The same effect changes the appearance of the sun itself. As the spacecraft races away, light coming from behind is redshifted, so the sun's spectrum would be pushed toward longer wavelengths in the traveler's frame. At sufficiently high speed, some visible light could shift towards infrared, and the whole rearward sky would be altered by the motion of the ship. The sun would not simply become fainter because of distance. Its light would also arrive differently because the crew is moving away from it so rapidly. The stars ahead would undergo the opposite kind of change, with incoming light shifted toward higher frequencies. But that transformation becomes more important later, when the ship reaches its extreme cruising speed. Near the beginning, the psychological meaning is simpler. The universe in front is becoming the direction of the future, while the universe behind contains everything the crew once considered home. If the travelers look back through a powerful telescope, they are also looking into Earth's past. Light leaving the planet after the spacecraft departs must travel outward and catch them, so every image of home carries a delay that grows with distance. The Earth they see is not the Earth that exists at that instant in some universal sense. It is the Earth whose light has finally reached their location. This turns distance into a barrier to certainty. The crew can know what Earth was doing, but not what Earth is doing now. A government could change, a city could be rebuilt, a scientific discovery could transform society, or an entire civilization could alter its course. And the travelers would continue receiving older information for years or decades of their own experience. The people on Earth face the same problem in reverse. They watch the spacecraft through signals that left it earlier, so mission control never sees the crew exactly as they are at that moment. As the gap grows, the idea of controlling the mission from home becomes increasingly unrealistic. Instructions sent from Earth are based on old information about the ship, and by the time those instructions arrive, the situation aboard could already be completely different. A 1,000-light-year mission therefore cannot depend on real-time support. The crew has to make decisions locally, repair equipment locally, and solve problems without waiting for anyone to answer. Earth can still send knowledge, but it becomes a library, arriving slowly from the past, rather than a control room guiding events as they happen. This would affect the emotional meaning of every message. A birthday greeting could arrive years late. A recording from a parent might be received when the sender is already elderly or gone. News about Earth could describe events that have long since been replaced by others. The farther the ship travels, the more communication begins to resemble opening historical documents, rather than speaking with people who share the same present. This is one of the quieter costs of extreme interstellar travel. The ship can carry enough food, air, power, and technology to keep people alive, yet no engineering can carry the social world they left behind into the same present. Photographs and recordings preserve memories, but the living civilization continues without them, and the travelers continue without it. Relativity makes that separation even more severe once the ship approaches the speeds required for a human lifetime. The travelers may experience only a few decades, while more than 1,000 years pass on Earth during the full crossing. This means the people they know do not merely become distant. They become part of history, while the crew remains biologically much closer to the age at which they departed. The sun would provide a physical version of the same change. For a long time, navigational instruments could continue identifying it as a known star behind the spacecraft, but visually, it would become less impressive with distance. Several light years out, the sun would still be detectable, yet nothing about its tiny appearance would reveal that one of its planets once contained every person the crew had ever known. Farther away, the constellations themselves begin to change, because the spacecraft is viewing the local stellar neighborhood from a different position. The familiar patterns seen from Earth are not permanent drawings fixed onto a distant sphere. They are perspective effects created by stars lying at very different distances. As the ship moves tens and then hundreds of light years away, those angles change, and the night sky stops looking like the sky in which the crew grew up. Some stars that appeared close together from Earth would separate widely. Others would move into new alignments. Bright stars might remain recognizable by their properties, but the shapes of familiar constellations would gradually dissolve. The crew could still reconstruct the old sky with software, yet looking through a window would no longer provide the same map their ancestors used for navigation and storytelling. The psychological transition may happen long before the midpoint. Early in the mission, the crew thinks of itself as leaving Earth. Later, it may feel more accurate to say they are traveling towards somewhere else, because Earth no longer dominates their environment. Communication is no longer current, and the direction behind them contains only delayed light. That does not mean the crew would forget where they came from. If anything, the distance could make Earth more important symbolically, because it is no longer available physically. Every stored image, every recording, every familiar object brought aboard would carry more meaning once the real planet can no longer be seen directly. The spacecraft itself becomes the only immediate human environment left. Its walls define breathable air, its systems provide water and power. And every person aboard lives inside the same artificial space while the natural world that shaped human biology disappears behind them. The ship is no longer transportation in the ordinary sense. It is the only place where human life exists within their reachable universe. Outside those walls, interstellar space appears empty and calm. Stars remain scattered across the sky. There is no visible atmosphere rushing past, and at constant speed the crew feels no motion at all. Nothing about the view would necessarily suggest that the spacecraft is moving fast enough to cross enormous distances within one human lifetime. That calm appearance is deceptive. The space between stars contains thin gas, dust, charged particles, and radiation, all of which are nearly harmless to a slow object compared with what they become when the ship meets them at relativistic speed. A single hydrogen atom carries very little energy when drifting through ordinary space, but from the perspective of a spacecraft moving close to light speed, the encounter can be far more energetic. Dust is more troubling because even a microscopic grain has vastly more mass than an individual atom. At low speed, it might leave a small mark. At a large fraction of light speed, the energy released in an impact can become serious enough to damage shielding or produce showers of secondary particles. The ship cannot steer around every grain because the particles are too small and too numerous to detect individually at useful distances. This is the point where the emptiness ahead stops being just a background and starts becoming part of the engineering problem. The same speed that allowed the crew to leave the solar system within a reasonable span now changes the meaning of every particle waiting in the darkness. And once the solar system has faded behind the ship, and there is no longer anything nearby that feels like home, the most dangerous part of the journey may come from the space that still looks completely empty in front of them. Interstellar space is often described as a vacuum, and compared with the atmosphere of Earth, that description is fair. But a vacuum is not the same as nothing. Between the stars, there are still atoms of hydrogen and helium, traces of heavier elements, microscopic dust grains, charged particles, and radiation moving through the galaxy. At the speeds of ordinary spacecraft, most of this material is so thin that a vehicle can cross it with very little trouble. At a large fraction of the speed of light, the same environment becomes something else entirely, because the danger comes not from how much material is there, but from how much energy the spacecraft carries into every encounter. A single hydrogen atom is almost unimaginably small. Yet, from the point of view of a ship moving at relativistic speed, that atom arrives with enormous kinetic energy compared with an ordinary collision. The spacecraft does not need to hit a dense cloud for this to matter. It can be moving through what astronomers would still call extremely thin gas, while countless individual particles strike the forward-facing surfaces at velocities no engineering material has ever experienced over long periods. The effect would be continuous rather than spectacular. There would not necessarily be one dramatic impact that announces the danger, because most interactions would happen at microscopic scales, heating material, damaging atoms in the shield, and producing secondary particles that can travel farther into the spacecraft. Over a journey of 1,000 light-years, the question becomes how much cumulative damage the front of the ship can absorb before the protection begins to fail. Dust creates an even more serious problem because a dust grain may contain billions or trillions of atoms bound together into one small object. A grain too small for a human eye to notice can carry enormous energy when the relative speed approaches that of light, and the spacecraft may have only fractions of a second to deal with anything detected directly ahead. At sufficiently high speed, Even a particle that seems harmless in ordinary life can strike with the violence of a much larger object moving slowly. This is one reason a relativistic spacecraft could not simply have a thin metal wall facing forward. The front of the vehicle would have to be designed as a sacrificial region capable of absorbing impacts, spreading energy, and preventing fragments or radiation from reaching the crew compartment. Engineers have proposed ideas ranging from thick layers of material to replaceable shields, clouds of particles released ahead of the ship, magnetic fields for charged particles, and combinations of several methods, but each solution adds mass and complexity to a vehicle that is already extraordinarily difficult to accelerate. A thick physical shield sounds simple until its mass is included in the propulsion problem. Every additional kilogram of protective material must be accelerated to the same extreme velocity as the rest of the ship, and later slowed down again at the destination. If the safest shield is made thicker, the ship becomes heavier. If the ship becomes heavier, the energy requirement rises. And if the propulsion system grows to provide that energy, the vehicle becomes heavier again. Protection and propulsion become locked together in a cycle where solving one problem makes another more difficult. The shield would also need to survive for the entire crossing, rather than only for a brief burst of speed. At 99% of light speed, the journey still lasts more than 1,000 years from Earth's frame, while the travelers may experience a much shorter interval because of time dilation. The spacecraft, however, continues interacting physically with the material along the full 1,000 light-year path, which means the forward surface has to endure every particle encountered between departure and arrival. The interstellar medium is not perfectly uniform either. Some regions contain lower densities, while others contain more gas and dust, and a route that looks acceptable in one direction could become much more dangerous if it crosses a denser cloud. A crewed mission would therefore need detailed knowledge not just of the destination, but of the space between here and there, mapping material that is difficult to observe precisely, even with modern astronomy. At low speed, a ship can afford to react to conditions as it finds them. At relativistic speed, reaction time becomes much shorter because anything ahead approaches so quickly. A large object detected too late cannot be avoided with a gentle turn, since changing course means changing the momentum of a spacecraft already moving at an extreme velocity. The safest strategy would be to know as much as possible about the route long before entering it. Yet 1,000 light-years contains far more space than any mission has ever needed to characterize in detail. There is also a limit to what sensors can see. A grain of dust is tiny and dark, and detecting it at useful distances while moving close to the speed of light would be extremely difficult. By the time reflected light from the particle reaches the spacecraft, there may be too little time to maneuver, even if the object can be identified. The ship cannot depend on steering around every threat, which makes shielding essential rather than optional. Gas atoms produce a different kind of problem because they are too numerous to avoid individually. The front of the spacecraft would effectively move through a thin stream of high-energy particles created by its own velocity. From the crew's frame, ordinary interstellar hydrogen can arrive with energies comparable to forms of radiation that require serious protection. And collisions with the shield can generate additional particles that continue deeper into the structure. This means the hull has to protect the crew from two sources at once: radiation already present in space, and radiation created because the spacecraft is moving so fast through matter. The faster the ship travels, the more severe the second problem becomes, which produces another uncomfortable trade. Increasing speed shortens the traveler's experience journey through relativity, but it can also make the external environment more dangerous. Natural cosmic rays already pose a challenge for long-duration human spaceflight, because energetic particles can pass through tissue and damage cells. 1,000 light-year mission cannot avoid that background simply by leaving the solar system, and outside the protective influence of Earth's magnetic field and atmosphere, the crew depends entirely on the spacecraft for shielding. At relativistic speed, the directional radiation created by the ship's motion adds another layer to an already difficult problem. The shield cannot be treated as a simple wall that stops everything. High-energy particles can penetrate material, scatter, and produce showers of secondary radiation, so making protection thicker does not always reduce danger in a perfectly straightforward way. The design has to consider what happens when particles enter the shield, where their energy goes, and what new particles are created during the collision. A human crew makes this harder because biological tissue is sensitive in ways machinery is not. Electronics can be hardened, duplicated, or shut down temporarily, while people have to remain alive continuously for years or decades of experienced travel time. Even small increases in long-term radiation dose matter, and the spacecraft would need safe living areas where the most important shielding surrounds the places the crew spends most of its time. The direction of travel would matter most. The forward side of the spacecraft faces the incoming interstellar material, so the strongest protection would likely be concentrated there. With the crew compartment placed behind layers of shielding and equipment, the ship might look less like a sleek science fiction vehicle and more like a protected bunker being pushed through space, with its most vulnerable systems hidden deep behind a heavy nose. That nose would slowly change over the journey. Impacts could vaporize tiny amounts of material, roughen surfaces, and alter coatings, while the ship's engineers would need a way to monitor how much protection remains. If the shielding is designed to be sacrificial, the spacecraft may have to carry enough material to lose part of itself gradually over hundreds of light years without exposing the crew. The dangerous environment would not remain equally severe throughout the mission, because the relative energy of collisions grows with speed. Early in the journey, while the ship is still accelerating, dust and gas are less threatening. Near the highest velocity, the same particles become far more energetic, and later, as the spacecraft slows near the destination, the danger gradually falls again. The middle of the journey could therefore be the most physically hostile part, even though it appears visually uneventful. The crew may be hundreds of light years from any nearby star, living inside a quiet cabin with no sense of motion, while outside the forward shield, a stream of particles strikes with energies created almost entirely by the spacecraft's own velocity. That contrast is important because speed changes the meaning of emptiness. A slow ship sees interstellar space as a thin environment it can cross gradually. A relativistic ship turns that same thin environment into a continuous high-energy collision experiment. Nothing about the space ahead has become denser. The spacecraft has simply made every encounter more violent by moving faster. Light itself also changes from the crew's perspective. Radiation arriving from ahead is blue-shifted toward higher frequencies, while light from behind is red-shifted, and the effect becomes stronger as the spacecraft approaches light speed. This means background radiation that is harmless in one frame can be shifted into more energetic forms in the traveler's frame, adding to the challenge of protecting both people and instruments. Even navigation becomes connected to shielding, because the ship may prefer routes with lower gas and dust density, rather than the geometrically shortest path. A slight detour could reduce the amount of material encountered, yet any change in route adds distance, demands course corrections, and affects the future position where the spacecraft meets its destination. The safest route may not be the straightest one. There is an unsettling irony in this balance. The crew needs extreme speed, because without it the journey lasts longer than a human life. But every step toward that speed makes the spacecraft harder to protect. The solution to the time problem creates a shielding problem, and the shielding needed to solve that problem adds mass that creates an energy problem. At lower relativistic speeds, engineers could imagine thicker shields and larger safety margins, but the journey experienced by the crew becomes longer. At higher speeds, time dilation becomes more useful, yet impacts become more energetic, and the energy needed to accelerate the ship rises dramatically. There is no obvious point where every requirement becomes easy at once. The 1,000 light-year distance magnifies these compromises because small inefficiencies persist for a very long path. A shield that loses a tiny amount of material per light-year may lose a significant fraction by the time the ship approaches the destination, while a small navigation error can become enormous after hundreds of light-years. The vehicle must be designed not merely to survive one high-speed event, but to remain reliable through an entire interstellar environment. By the time the crew has traveled far enough that Earth is only delayed information behind them, their survival depends on layers of engineering that have never been tested at anything close to this scale. The outside world may look calm, but the spacecraft is continuously converting its enormous velocity into impacts, radiation, heat, and material damage. And once the ship has been given enough shielding to survive the space ahead, another problem becomes impossible to avoid. Because every kilogram protecting the crew has to be accelerated across 1,000 light-years, and the energy required to do that may be even more difficult than the dangers of the journey itself. At ordinary speeds, it is easy to imagine energy as something a spacecraft uses simply to keep moving. But in deep space, the largest cost comes from changing velocity. Once a ship has reached its cruising speed, it can continue coasting without an atmosphere slowing it down. Yet reaching a large fraction of the speed of light requires an extraordinary investment of energy at the beginning, followed by another enormous change in velocity when the spacecraft finally has to slow near the destination. The difficulty rises sharply because special relativity changes the relationship between speed and energy. A conventional vehicle can gain speed in a way that still feels intuitive, but near the speed of light, each additional increase becomes more expensive than the one before it. The spacecraft can approach light speed more and more closely, but an object with mass cannot be accelerated all the way to that limit with any finite amount of energy. That is exactly where the human mission wants to operate. The faster the ship moves, the more strongly time dilation can reduce the duration experienced by the crew, but the energy requirement becomes most severe in the same regime. A speed that makes 1,000 light-years fit inside a human lifetime is therefore not merely faster than present technology. It belongs to a part of physics where every small increase in velocity can have an enormous engineering cost. The total mass of the ship makes that problem worse. A human spacecraft cannot be a bare probe carrying only a camera and transmitter, because the crew needs breathable air, water, food, medical equipment, computers, spare parts, power systems, living space, propulsion hardware, and the heavy shielding required to survive radiation and interstellar impacts. Every one of those systems has to be accelerated to the same velocity. Protection becomes especially expensive because one of the simplest ways to reduce radiation or impact damage is to place more material between the crew and the outside environment. A thicker shield may make the ship safer, but it also makes the ship heavier, and that extra mass requires more energy to accelerate. If additional fuel is carried to provide that energy, the fuel itself adds mass and must also be accelerated. This means the spacecraft cannot be designed as a collection of separate problems. The shield affects the engine affects the mass affects the energy requirement, and the energy system affects the cooling system. A decision made to protect the crew at the front of the vehicle can change the size of the propulsion system at the rear, while every backup system introduced for reliability creates another mass that has to be pushed toward relativistic speed. Chemical rockets are nowhere close to the energy density required for such a journey, which is why serious interstellar concepts tend to move toward fusion, antimatter, or propulsion powered by energy delivered from outside the spacecraft. None of these currently offers a practical human vehicle capable of crossing 1,000 light-years, but they show how far the mission has moved beyond the technology used to reach the moon or the outer planets. Fusion is attractive because nuclear reactions can release vastly more energy per unit mass than chemistry, And in principle, that energy could be used to produce high-speed exhaust. A working fusion spacecraft, however, would need to control the reaction, direct enough of its energy into thrust, remove waste heat, carry suitable fuel, and operate reliably for years of acceleration and deceleration without the maintenance infrastructure available on Earth. Antimatter offers an even greater theoretical energy density because matter and antimatter can convert a large fraction of their mass into energy when they meet. The practical obstacles are equally extreme. Producing large quantities would itself require enormous energy. Storing antimatter safely would demand systems that prevent it from touching ordinary matter. And converting the resulting radiation and particles into controlled thrust would be a major engineering challenge. Even an ideal energy source cannot accelerate a ship merely by existing on board. The spacecraft still has to exchange momentum with something, whether by throwing reaction mass backward, interacting with a field, or receiving momentum from an external beam. This is why the design of the propulsion system matters as much as the amount of energy available. Beamed propulsion tries to reduce the burden carried by the vehicle by placing the main power source elsewhere. A powerful installation near the solar system could direct a laser or another beam toward a sail, pushing a lightweight spacecraft without requiring it to carry all of its own fuel. This idea is especially appealing for tiny robotic probes where mass can be reduced to the minimum. A crewed ship changes the situation because shielding, life support, and living space cannot be reduced to a tiny payload. The beam would have to accelerate a much heavier vehicle, remain accurately aimed as the spacecraft recedes, and somehow be paired with a method of slowing the ship near a destination 1,000 light-years away. A beam from home may help with departure, but it does not automatically solve arrival. Braking is easy to underestimate, because the journey is usually imagined as a long period of forward motion. Yet a spacecraft traveling near light speed cannot simply reach the destination and stop. If no braking system exists, the ship would cross the target region at almost the same enormous velocity it carried through interstellar space, turning a mission intended to reach another system into a brief flyby. Carrying fuel for deceleration means carrying that mass from the beginning and accelerating it during the entire outbound journey. Building braking infrastructure at the destination assumes something is already there to help. Other ideas, such as magnetic sails interacting with plasma or stellar winds, may offer ways to remove velocity without carrying all of the necessary reaction mass. But slowing a large relativistic ship remains one of the hardest parts of the mission. The energy problem, therefore, appears twice. The civilization sending the crew has to provide the ability to reach the required speed, while the spacecraft must also preserve enough capability to lose that speed safely. Navigation corrections, emergencies, and small changes in trajectory add further demands, so the energy budget cannot be calculated as though every part of the journey goes perfectly. No real propulsion system is perfectly efficient either, which means some of the energy inevitably becomes heat. On Earth, machines can transfer heat into air, water, or the ground, but a spacecraft in vacuum has to radiate it away. Powerful engines and onboard systems may therefore require large radiators, and those structures add mass while also creating surfaces that must survive the same interstellar environment as the rest of the vehicle. The ship can try to use its mass efficiently by giving materials several jobs at once. Water stored for the crew can also contribute to radiation shielding. Supplies can be arranged around living areas, and structural components can be placed where they protect more vulnerable systems. At relativistic speed, unused mass becomes extremely expensive, so almost every kilogram would need a clear purpose. The number of people aboard would matter for the same reason. More crew members provide redundancy, knowledge, and social stability, but they also require more space, water, food, life support, and shielding. A smaller crew reduces mass while making the mission more vulnerable if one specialist becomes ill or dies. Human factors and propulsion would become connected in a way that does not happen on ordinary journeys. This creates a strong reason not to chase the highest possible speed, simply because the physics permits it. A slightly slower ship might require less energy, face less severe dust impacts, and need less extreme shielding, even though the crew experiences a longer journey. A faster ship gives stronger time dilation, but moves every engineering problem into a more difficult range. The best mission might therefore be built around compromise. A civilization could accept several decades of traveler time, instead of trying to reduce the crossing to the shortest possible duration, if that allows a meaningful reduction in velocity, energy, shielding mass, and risk. Relativity makes the journey possible in principle, but engineering would decide how much of that theoretical advantage is actually worth buying. The scale of the civilization behind the mission would also matter. Accelerating a large human spacecraft to relativistic speed could require an industrial effort far beyond present spaceflight, especially if the plan involves enormous fusion facilities, antimatter production, or powerful beamed propulsion systems. The mission would not be only a vehicle. It could depend on a network of energy generation, manufacturing, tracking, and support infrastructure larger than anything built for exploration today. That difference between physical possibility and practical capability is important. Special relativity does not forbid a massive spacecraft from traveling at a large fraction of light speed, but it makes clear why such a journey cannot be treated as an enlarged version of a modern rocket launch. The energies, masses, timescales, and failure consequences all change together. Once the ship finally reaches its selected cruising speed, the crew may experience something unexpectedly calm. If the engines stop thrusting, there is no sensation of velocity inside the cabin, because constant motion by itself does not create a force that the body can feel. A person could sit quietly, watch a clock tick normally, and have no direct physical sensation that the spacecraft is crossing hundreds of thousands of kilometers every second relative to Earth. The enormous energy invested in the vehicle is now hidden in its motion. The walls do not glow merely because the ship is fast. Conversations sound normal, and everyday objects behave according to the local conditions inside the spacecraft. Without looking outside or checking instruments, the crew could live through ordinary moments while carrying a kinetic energy that would be almost impossible to imagine on Earth. The evidence appears in the light beyond the hull. At relativistic speed, stars ahead and behind no longer send their light to the spacecraft in the same way they did near Earth. Frequencies shift, apparent directions change, and the familiar arrangement of the sky becomes distorted by the motion of the ship itself. And once the engines have spent enough energy to carry the ship into true relativistic flight, the next change would be visible through every window and detector. Because at those speeds, even the light of the universe begins arriving from different directions and in different colors. At ordinary spacecraft speeds, motion barely changes the appearance of the stars. A probe can cross the solar system at tens of kilometers per second and still see the same broad patterns visible from Earth, because those velocities are tiny compared with the speed of light. A ship moving at a large fraction of light speed would be different. The stars themselves would not suddenly rush toward the bow, yet the directions from which their light appears to arrive would shift because of relativistic aberration, gradually pulling more of the visible sky toward the direction of travel. The effect would strengthen as the spacecraft accelerates. Objects that would normally appear far off to the sides begin shifting forward in the crew's view, while the rearward sky seems stretched outward. At extreme speed, a much larger fraction of the surrounding universe can appear concentrated into a smaller region ahead, even though the spacecraft is still physically surrounded by stars in every direction. This would not look like the familiar image of long white streaks racing past a window. Distant stars would still appear as points unless the ship's instruments or displays deliberately turned their motion into trails. The real change is subtler and stranger. The points themselves occupy different apparent directions, and the entire geometry of the sky becomes distorted by the observer's motion. Relativistic aberration happens because every observer still measures light, moving at the same fundamental speed, while observers moving relative to one another do not have to agree on the angle from which a particular ray arrives. For the crew, light that would strike a slower observer from the side is received while the ship is moving rapidly forward, so the apparent arrival direction shifts toward the bow. The constellations would already have changed simply from traveling hundreds of light years away from Earth, and relativistic aberration would distort that new arrangement again. Stars that once formed familiar shapes would be viewed from a different part of the galaxy, then compressed toward the forward direction by the ship's motion. Color would change as well. Light arriving from ahead would be shifted toward higher frequencies through the relativistic Doppler effect. Visible light from a star could move toward blue and ultraviolet, while radiation that began in infrared could shift upward into the visible range. At sufficiently high speeds, some radiation that was harmlessly outside human vision could be moved into more energetic parts of the spectrum. Behind the ship, the opposite would happen. Light from the sun, Earth, and the stars the crew is leaving would be redshifted toward lower frequencies. Visible light could shift towards infrared, and the rearward sky would appear increasingly altered as the spacecraft continues accelerating away from it. The sources themselves have not cooled or changed color. The difference comes entirely from the motion between source and observer. This means a direct view through a conventional window would not be enough to understand the environment. Human eyes are sensitive only to a narrow band of the electromagnetic spectrum, and at relativistic speed, much of the useful information could shift outside that band. A realistic spacecraft would need sensors covering infrared, visible, ultraviolet, and higher energy radiation. Then, software to translate what those instruments receive into something the crew can interpret safely. The display could show the sky in two different ways. One mode might present the radiation as it actually arrives on board, revealing the forward concentration and severe color shifts produced by speed. Another could mathematically correct for the spacecraft's motion and reconstruct how the same stars would appear to a slower observer, giving the crew a more familiar map for navigation. That correction would be essential because the apparent direction of a star would no longer match a simple stationary star chart. NASA already treats stellar aberration as a real navigational effect when precise spacecraft pointing is required. Although present missions move far too slowly for the distortion to become visually dramatic, on a relativistic ship, the effect would no longer be a small correction. It would be built into the way every camera and guidance system interprets the sky. The distorted star field could also help the spacecraft measure its own motion. If navigation software knows where many stars should appear in a reference frame, then the amount by which their apparent positions have shifted can reveal information about velocity. The strange sky would therefore serve not only as a visual consequence of relativistic travel, but as a navigation tool. The forward direction would become increasingly important for another reason. Relativistic motion can concentrate radiation toward the direction of travel, making the front of the ship the place where incoming light and particles are most strongly transformed. The same region already needs the strongest physical shielding against interstellar gas and dust, so the bow becomes both the most dangerous and the most information-rich direction in the entire spacecraft. A conventional transparent window facing forward would therefore be difficult to justify. It would need to survive high-energy particle impacts while also emitting radiation that may have been shifted into unsafe wavelengths. A practical design would probably protect the crew behind solid shielding and use external sensors instead, creating the view electronically inside the cabin. That would make the visual experience strangely calm. The crew might sit in a quiet room while a display shows a universe compressed toward the bow, with stars ahead shifted toward higher frequencies and the rearward sky sliding toward red. There would be no wind, no vibration required at constant speed, and no physical sensation that the ship is moving hundreds of thousands of kilometers per second relative to Earth. The human body would not feel relativistic velocity because constant motion alone does not create a force. Once acceleration stops, a person aboard can move normally, eat normally, sleep normally, and watch a clock tick at an ordinary rate. Nothing inside the cabin announces that the outside universe is being observed from a frame moving close to the speed of light. Only external measurements reveal how unusual the situation has become. A star ahead can appear in a different position and at a different frequency than expected from a slower frame, while a signal from Earth can arrive strongly redshifted from behind. The crew's local experience remains ordinary even as the sky shows that their relationship with the rest of the universe has changed. Communication equipment would have to adapt to this. A radio signal sent from Earth toward the spacecraft would be received at a lower frequency because the ship is racing away from the source, while signals arriving from the destination ahead would be shifted upward. Engineers would have to know the expected relativistic Doppler changes so receivers can find and decode transmissions that no longer arrive near their original frequencies. The destination ahead would also look different from the image astronomers studied before launch. Because the ship is racing toward it, the system's light would be blue-shifted. And because the spacecraft is closing the distance rapidly, it would receive progressively newer information from that star system. The travelers would be moving into the destination's more recent history. Earth behind them would feel like the opposite process. Its light and signals are chasing the spacecraft from the rear, arriving red-shifted and increasingly disconnected from whatever is happening there at that moment. The crew can still receive information from home, but every message belongs to a past version of Earth, and the relativistic motion changes the rate at which that information arrives. This creates an unusual divide. Ahead lies a system whose newer history is arriving faster as the ship approaches it. Behind lies a world whose light is stretched and delayed. The spacecraft is moving between two histories, leaving one behind while physically entering another. The sun would become part of that rearward history. Even if instruments can identify it precisely, its light would no longer arrive the way it did near Earth. Distance makes it fainter, motion shifts its spectrum, and the changing stellar perspective places it inside a sky that no longer resembles the constellations of home. As the journey continues, the spacecraft could use corrected imagery to track the target star's true future position. Relativistic aberration changes apparent directions, while ordinary stellar motion changes where the target actually is over centuries of Earth time. Navigation has to separate these effects carefully, so that the ship does not confuse a motion-induced visual shift with a real error in trajectory. The farther the spacecraft travels, the more this matters, because small angular mistakes become enormous physical misses over hundreds of light years. At relativistic speed, there is little room for casual correction near the end, especially if braking must begin far from the destination. The altered sky must be understood precisely enough that visual strangeness never becomes navigational confusion. As the ship begins decelerating, the sky would slowly change again. The forward concentration caused by aberration would weaken, Doppler shifts would become less extreme, and the stars would move toward the positions expected from the spacecraft's actual location rather than its high-speed motion. The universe would appear to open back out as the velocity falls. But the familiar sky of Earth would not return. Even after relativistic distortions fade, the spacecraft is physically hundreds of light years from the solar system. So the constellations remain different simply because the viewing position has changed. Correcting for motion cannot undo the distance that has already been crossed. This distinction is important because the crew could separate two kinds of change. Some distortions disappear when the ship slows, proving they were caused by relativistic motion. Others remain because the spacecraft has genuinely reached a different part of the Milky Way. The travelers have not only moved fast, they have moved far enough to change the geometry of the stellar neighborhood around them. The altered sky would therefore be one of the clearest signs that the voyage has entered a regime where ordinary intuition fails. Light no longer arrives from the directions or at the frequencies a person from Earth would expect, yet every observer aboard still experiences their own surroundings as normal. That contrast prepares the crew for an even stranger fact about the journey. Their clocks would also seem perfectly normal. A second inside the ship would still feel like a second, and no traveler would sense their own time slowing. People on Earth would say exactly the same thing about their clocks. The disagreement only appears when the two groups compare how much time has passed between departure and arrival. At 99.9% of the speed of light, Earth can measure 1,000 light-year crossing as taking just over 1,000 years, while the travelers experience only a small fraction of that duration. Nothing in the cabin feels slowed, and nothing on Earth feels accelerated. Yet both descriptions can be correct, because elapsed time depends on the path taken through space-time. The same relativity that bends the apparent star field toward the front and shifts colors across the spectrum is therefore also changing the relationship between the crew's clock and Earth's. The visual effects are not separate curiosities. They are part of the same deeper structure that makes the journey fit inside one human life from the traveler's point of view, while centuries pass elsewhere. And once the altered sky has shown the crew that their motion is changing the way light reaches them, the next change becomes even harder to ignore, because the same relativity that shifts the stars also means their clocks and Earth's clocks will no longer agree on how long the 1,000 light-year journey has taken. Nothing inside the spacecraft would announce this. By slowing down, a clock on the wall would tick normally, a heartbeat would feel ordinary, chemical reactions would proceed at their usual rates, and the crew would age in the same familiar way they always had. If someone spent 10 years aboard the ship, according to the onboard clocks, they would physically experience those 10 years. There would be no sensation of time being stretched or compressed around them. People remaining on Earth would say exactly the same thing about themselves. Their clocks would also tick normally. Their days would still last 24 hours, and no one standing on the planet would feel that time had suddenly begun racing ahead. Special relativity does not require one side to experience its own life as strange. The disagreement appears only when the histories of the travelers and Earth are compared after they have followed very different paths through space-time. At 90% of the speed of light, the effect is already real, but it is not yet enough to make 1,000 light-year crossing fit inside a human life. Ignoring acceleration and braking for the moment, Earth would measure a little more than 1,100 years for the ship to reach the destination, while the crew would experience roughly 480 years. That is a dramatic difference between clocks, yet it still leaves the travelers facing a journey several human lifetimes long. At 99% of light speed, the separation grows much stronger. Earth would measure a little over 1,010 years, while the travelers would experience roughly 140 years. The spacecraft has gained only 9 percentage points of speed compared with the previous example. But the change in experience time is enormous, because the relativistic effect increases rapidly as the velocity moves closer to the speed of light. At 99.9%, the crossing becomes something an individual human could at least imagine surviving. Earth would record just over 1,001 years between departure and arrival, while the travelers would experience about 45 years during an idealized constant-speed crossing. The people who launched the mission could enter the ship as young adults and reach the destination within their own biological lifetime, even though more than a millennium has passed for the civilization they left behind. Pushing the velocity to 99.99% produces an even stranger result. From Earth's point of view, the travel time changes by only about 1 year compared with 99.9%. because the spacecraft is already extremely close to the universal speed limit. For the crew, however, the experienced time could fall to roughly 14 years during the constant speed part of the journey. A tiny-looking change in the percentage produces a huge change in how much of a human life is spent aboard. These examples ignore the periods needed to accelerate and decelerate, so they are not complete mission plans, but they reveal what relativity makes possible. The universe does not allow the spacecraft to cross 1,000 light-years in less than about 1,000 years according to Earth, because the ship cannot outrun light. What changes is the amount of time accumulated along the traveler's own path. This is often described by saying that moving clocks run slow, but that phrase can be misleading if it suggests a broken clock or a traveler somehow feeling slowed down. The crew's clock is not malfunctioning. It measures the proper time along the spacecraft's journey, while clocks following a different path through space-time can accumulate a different amount before the two histories are compared again. The most useful way to feel the difference is to think about aging rather than machinery. Suppose a traveler leaves Earth at age 30 and experiences 45 years aboard the spacecraft before arrival. They would step out near the destination at around 75 years old. If Earth has measured a little more than 1,000 years during the same crossing, nobody who personally watched the launch could still be waiting for them. Children born generations after the departure could themselves live entire lives and vanish into history, while the traveler experiences only one lifetime. Languages could change, nations could disappear, technologies could become unrecognizable, and human society could transform in ways the crew cannot predict. The ship has crossed 1,000 light-years through space, but it has also moved more than a millennium away from the period of history in which it began. That separation is not caused by communication delay alone. Even if the crew had a perfect telescope and a perfect transmitter, no technology could make their elapsed time equal Earth's while preserving the same relativistic journey. Communication delay determines when information arrives, while time dilation determines how much time the two sides actually experience between departure and arrival. From the crew's perspective, the destination can also be described as closer along the direction of motion because of length contraction. The travelers do not measure the full 1,000 light-years in the same way that observers at rest relative to Earth and the destination do. At extreme speed, the distance along the direction of travel is contracted in the spacecraft's frame, which is another way of understanding how the crew can reach the destination in far less than 1,000 years without ever measuring themselves moving faster than light. The effect becomes more complicated when acceleration is included. A real crew would need time to speed up, perhaps using an acceleration comfortable enough for humans to tolerate, and later reverse that process to slow down. During those phases, the spacecraft passes through a continuous range of velocities, so the amount of time dilation changes throughout the trip, instead of remaining fixed at one value. If some future propulsion system could maintain an acceleration near one Earth gravity for a long period and then reverse to decelerate for the remaining distance, the crew could in principle cross 1,000 light-years in a surprisingly small amount of onboard time, because the ship would spend much of the route at an extreme relativistic velocity. Earth would still see a journey lasting a little more than 1,000 years, while the travelers might experience only on the order of years or decades, depending on the exact profile. That scenario is useful as a demonstration of relativity, but it also emphasizes how unrealistic the engineering remains. Maintaining such acceleration for years, supplying the required energy, shielding the ship at its peak velocity, navigating accurately, and then performing a matching deceleration would demand technology far beyond anything available today. The physics allows the clocks to disagree. It does not provide the machine needed to create that disagreement safely. For the crew, everyday life would continue at its own normal pace throughout the voyage. They might celebrate birthdays, repair equipment, grow older, and measure the passing years exactly as they would on Earth. A person could spend a decade working aboard the ship and genuinely experience a decade of memories, even while hundreds of years accumulate in Earth's frame during the same portion of the mission. The unsettling part is that no single moment aboard tells them how much history is passing elsewhere. The cabin remains quiet, and the clock does not suddenly jump forward whenever another century passes on Earth. The difference exists only in the relationship between the spacecraft and the distant planet, which makes the scale of the separation easy to calculate and much harder to imagine emotionally. The destination produces the opposite feeling. As the ship approaches it, that star system becomes increasingly immediate. Its light has less distance to cross, its position dominates navigation, and the spacecraft begins preparing to decelerate into a local environment that is becoming part of the traveler's present, rather than a remote astronomical target. The crew has therefore exchanged one present for another. They left a world with which they once shared daily life, crossed a relativistic path that reduced their own elapsed time, and approached a region of the galaxy whose current conditions become more directly accessible as the distance closes. Earth remains real, but it belongs increasingly to a different part of their personal timeline. This is why returning home would be unlike an ordinary round trip. If the crew eventually turned around and crossed the same distance again at relativistic speed, Earth could accumulate another millennium while the travelers age only decades more. They might physically return to the solar system and still find that the world they remember has disappeared in every social sense. Buildings, languages, institutions, family lines, and perhaps entire cultures could belong to archaeology. The planet might remain recognizable, yet almost nothing about human society on its surface would need to resemble what the crew left behind. Relativistic travel can bring the spacecraft back to the same place, but it cannot bring the travelers back to the same historical moment. That consequence makes time dilation more than a mathematical trick for shortening a journey. It turns relativistic travel into a one-way movement through history, even when the spacecraft is capable of reversing direction. The crew may be able to return to the location they left, but there is no engine capable of returning them to the time they left. A journey of 1,000 light-years therefore creates an unusual bargain. Relativity can make the distance survivable for an individual traveler, but only by allowing the outside world to age much more than the traveler does. The very effect that solves the human lifetime problem also guarantees that the relationship with Earth will be changed permanently. This is one reason the situation feels so unnatural. Human experience is built around speeds where relativistic differences are tiny, so we grow up assuming that everyone can agree on how long a trip took once communication delays are removed. At interstellar velocities, that assumption stops working, and a journey becomes partly defined by the path through time taken by the traveler. The crew would see the result most clearly near arrival. Their bodies may have aged by only several decades. The onboard calendar may still feel connected to the century of departure, and personal memories of Earth may remain vivid, yet the destination's local clocks and astronomical history would tell them that more than 1,000 Earth years have passed since launch. If they point a telescope backward, however, the view creates one final complication. Seeing Earth from 1,000 light-years away does not show the planet as it exists at the moment of arrival, because the light reaching the destination also needed roughly 1,000 years to cross the distance. The travelers can be living more than a millennium after departure in Earth's frame while looking back at photons that left the solar system near the period when their journey began. The planet in the telescope and the planet that actually exists are therefore separated by centuries of unseen history. The crew could arrive knowing that Earth has moved far into the future while still receiving an image of a much younger world, turning the direction of home into a literal view backward through time. And once the crew reaches the far end of the 1,000 light-year journey with only part of a lifetime behind them, Looking back toward Earth creates perhaps the strangest view of all, because the planet they see would not be the 1,000-year-older Earth that exists then, but an image that left home centuries earlier and has only just reached them. The reason is simple, even if the result feels deeply unfamiliar. Light does not show us distant places as they are at some universal present moment. It shows them as they were when the light began its journey. From a destination 1,000 light-years from Earth, the newest light arriving from the solar system is already roughly 1,000 years old by the time it reaches the observer. That does not mean that travelers could casually watch cities, oceans, or people through an ordinary telescope. Earth would be extremely faint, very close to the glare of the sun, and impossibly small to resolve in detail with anything resembling present technology. The important point is not that the crew would have a perfect video of the past, but that every photon reaching them from Earth would carry information from an earlier period. If the spacecraft crossed the distance at an idealized constant speed of 99.9% of light speed, Earth would measure just over 1,001 years between departure and arrival. At the moment the travelers reach a point 1,000 light-years away, the newest light from Earth arriving there would have left the planet only about 1 year after launch. Everything Earth experienced during the remaining 1,000 years would still be somewhere behind that light, traveling across the darkness toward them. The contrast is remarkable. The crew could arrive knowing that more than a millennium has passed on Earth, while the light available from home still belongs to nearly the same era in which they departed. A sufficiently advanced observatory looking backward would not reveal the true 1,000-year-older Earth that exists at that moment. It would receive an image of a much younger planet, because the newer light has not had enough time to cross the distance. At 99% of light speed, the exact relationship changes slightly. The crossing takes a little more than 1,010 years in Earth's frame. So the newest Earth light arriving at the destination around the moment of arrival would have left roughly 10 years after launch. At 99.99%, the difference becomes even smaller, and the arriving light would come from only a short time after departure. The faster the ship moves toward the speed of light, the more closely its Earth frame travel time approaches the 1,000-year light travel time itself. The spacecraft can never catch or outrun the photons that left Earth at departure, but it can follow not far behind them across the entire distance. That is why the travelers can move far into Earth's future, while still arriving alongside light from the beginning of their own mission. During the voyage, messages from Earth would reveal the same effect. Suppose the planet continues transmitting after launch, while the spacecraft races away at 99.9% of light speed. A signal sent 1 year after departure is moving only slightly faster than the ship, so it can spend almost the entire journey trying to catch up before finally reaching the travelers near the far end. The crew would therefore not watch 1,000 years of Earth history rush past in a compressed stream during their 45 years on board. During an idealized high-speed cruise, they might receive only a small amount of post-departure Earth history before reaching the destination. Information from later centuries remains behind them, still crossing the same enormous gap. A message transmitted 100 years after launch would not be waiting for the spacecraft at arrival. It would need 1,000 years to cross from Earth to the destination, reaching that system around 1,100 years after departure. By then, the original travelers might have been living there for generations of local time, if they and their descendants were still present. Communication at that distance stops behaving like conversation and begins behaving more like a slow exchange between eras. The travelers can still send data, observations, and messages, but they do so knowing that the recipients may belong to societies that do not yet exist. Earth can send information outward as well, yet every response arrives after the world that created it has already moved far beyond that moment. The crew could build an observatory and continue watching the delayed solar system light arrive year after year. In principle, Each additional year spent at the destination would reveal roughly another year of Earth's old history. The travelers might slowly receive astronomical evidence of changes around the Sun, or detect powerful transmissions sent after their departure. But all of it would describe events that happened around 1,000 years earlier in Earth's frame. There is no paradox in this. The message does not preserve the person who created it. It simply took a very long time to arrive. Astronomy already works this way whenever we observe distant stars and galaxies. The difference here is that the delayed light is coming from the traveler's own home, turning an ordinary property of the universe into something deeply personal. Even with extremely advanced instruments, the travelers could not use a telescope to skip ahead and reveal what happened on Earth after the light currently reaching them was emitted. The missing information simply has not arrived yet. No improvement in optics can collect photons that are still hundreds of light years away. That limitation makes the separation more severe than a simple communications problem. If Earth suffered a major disaster 500 years after launch, the crew would have no way to know about it when they first arrived. Evidence of that event would still be halfway through the journey toward them. For centuries after arrival, old Earth light could continue looking normal before the information about the disaster finally appeared. The same is true for positive changes. Humanity could have spread across the solar system, built enormous structures, transformed the planet, or developed technologies that make the original spacecraft seem primitive, yet none of those developments would be visible immediately from the destination. The crew begins life in the new system with a picture of home that is already ancient. This means Earth cannot remain a practical source of support. If something fails after arrival, and the crew asks for help, the request needs 1,000 years to reach the solar system. Even an immediate answer requires another 1,000 years to come back. By the time the solution arrives, the original problem would belong to a distant past. The travelers, therefore, have to treat the destination as a place of complete local independence. Their ship must be able to repair itself. Their settlement must produce what it needs. And every important decision has to be made without expecting timely help from home. Earth remains culturally important, but operationally, it has become unreachable. The destination, meanwhile, becomes the exact opposite. Before launch, every observation of that star system was also delayed by roughly 1,000 years. Astronomers on Earth were choosing a target based on ancient light, studying planets and stellar conditions as they existed centuries before the mission began. As the spacecraft moves toward the target, it receives progressively newer light because it is closing the distance. The system slowly reveals a more recent version of itself, and by the time the ship arrives, the crew can finally measure local conditions without the huge delay that limited observers on Earth. A planet that was once only a faint signal becomes a world that can be examined from nearby. This creates a strange asymmetry between the crew and the civilization left behind. The travelers can study the destination in its local present, while people on Earth, at the same Earth frame moment, still see that system as it was about 1,000 years earlier. If the spacecraft enters orbit, lands, or begins building a settlement, Earth will not see evidence of those events until another millennium has passed. The mission planners therefore never had access to the exact destination the crew eventually reaches. They had access to an earlier version of it. A star that appeared quiet could have changed during the hidden centuries. A planetary atmosphere might have evolved. Or an unexpected object could now exist where old observations showed nothing important. The last part of the voyage would slowly remove that uncertainty. As the ship decelerates, relativistic distortions weaken, the target star settles into a more ordinary appearance, and local planets become easier to measure. What began as a statistical description of a distant system becomes direct observation of the actual environment the crew is entering. That transition may be one of the most important moments in the entire journey. For most of the mission, the destination is something calculated from old light and predicted motion. Near arrival, it becomes a real place with current weather, current radiation, current orbital positions, and current hazards that no observer on Earth has ever seen in real time. The travelers would also discover how much the local sky has changed. The Milky Way is still the same galaxy, but the pattern of nearby stars is different from the one seen around the Sun. Familiar constellations have lost their shapes. The solar system sits in a distant direction behind them, and the target star now dominates a region of space that once existed only as a point on a chart. 1,000 light-years is not enough to leave the Milky Way or reach some completely separate cosmic environment. The crew is still inside the same broad galactic disk, surrounded by stars, gas, dust, and the gravitational structure of the galaxy. Yet the distance is large enough that the local neighborhood can feel completely unfamiliar. Whether the destination contains planets suitable for exploration would depend entirely on the system chosen. The title does not guarantee another Earth or even a habitable world. The travelers could arrive near a quiet star with barren planets, a system filled with radiation, a region with no useful worlds at all, or something more promising than expected. That uncertainty matters because a journey of this length cannot rely on discovering the truth only after arrival. Mission planners would choose the target using the best remote observations possible, perhaps over many years, but the 1,000-year light delay means those observations are always historical. The spacecraft is ultimately traveling toward a future version of a system that Earth cannot directly inspect. By the time the crew reaches it, they may be the only humans who know what that place actually looks like now. Their measurements could be precise and immediate, yet every discovery they transmit home begins another 1,000-year journey before anyone on Earth can receive it. A new planet could be found, photographed, mapped, and explored, while Earth remains unaware for centuries. A settlement might grow, fail, or change completely before its earliest images reach the solar system. The history of the destination could unfold locally long before its beginning is visible from home. That makes the crew less like distant explorers reporting to a control room and more like the founders of an isolated branch of history. They still come from Earth, but the information boundary created by distance ensures that their future and Earth's future can develop almost independently. Behind them, the solar system continues sending ancient light. Ahead of them, the destination becomes immediate. The journey has carried the travelers across enough space that these two directions no longer belong to the same practical present. And once Earth has become a 1,000-year-old image behind the spacecraft, the journey finally turns toward the place in front of it, where the crew must discover what is actually waiting 1,000 light-years from home. By the time the ship begins its final deceleration, the destination would no longer be a point on a star chart. The target star would grow steadily more important in the sky. Surrounding objects would separate from the background, and instruments would begin resolving a system that had once existed only through distant observations. For the crew, this would be the first moment when the destination starts behaving like a real place rather than a prediction. That distinction matters because everything known before launch came from old light. A system 1,000 light-years from Earth was observed as it existed roughly 1,000 years earlier, and even the most careful mission planners could not see its true present before departure. During the voyage, the spacecraft would receive progressively newer information as it moved closer, but the final details could only be known when the ship actually arrived. A stable star would probably still be recognizable, yet the smaller parts of the system could differ from the version mapped on Earth. Planetary atmospheres can change, moons can remain active, comets can move into new orbits, and small asteroids or dust structures may have been too faint to detect across such a distance. The crew would be entering a system whose broad shape was known, but whose current details were partly hidden. As the spacecraft slows, the relativistic distortions that dominated the forward view would begin to weaken. Doppler shifts would become less severe, aberration would relax, and the star field would settle into a shape determined mostly by the crew's new position in the galaxy rather than by extreme speed. The sky would become easier to interpret, but it would not become familiar again. The constellations seen from Earth are perspective effects produced by stars lying at very different distances. Move 1,000 light-years, and those angles change dramatically. Some bright stars would remain recognizable by their properties, yet the familiar patterns used for navigation and storytelling would be distorted or gone. The crew would still be inside the Milky Way, but the night sky would belong to another part of it. The sun would sit somewhere behind them, as one faint star among many. Navigation software could identify it immediately, and powerful instruments could point toward it. But a person looking without assistance might have no reason to know which point was home. The star that once dominated every day of human life would now require a marker on a display. That is one of the clearest ways to understand what 1,000 light-years means. The travelers have not crossed the galaxy, and on a map of the Milky Way their journey is still relatively local, yet they have moved far enough for the visual language of home to disappear. The galaxy remains the same structure, while the human view of it has been completely rearranged. The destination star would become the new center of practical life. Its radiation, magnetic activity, brightness, and long-term stability would determine where the spacecraft can safely orbit and how much energy future habitats can collect. A system selected for settlement would probably favor a relatively stable star. But stability does not mean complete safety, because every star produces radiation and changes over time. The planets would be less certain. From Earth, astronomers might estimate their masses, sizes, orbital periods, temperatures, and perhaps parts of their atmospheres. Yet those measurements cannot reveal everything that matters to a human settlement. A world that looks promising from 1,000 light-years away may have violent weather, dangerous radiation, unexpected chemistry, or a surface that is far less stable than models suggested. Being inside a habitable zone would not solve that problem. The phrase only describes a region where liquid water could be possible under suitable conditions. It does not guarantee breathable air, a comfortable climate, or a safe environment. Earth and Venus already show how differently neighboring rocky worlds can develop around the same star. The crew could therefore arrive after the longest journey in human history and discover that there is no second Earth waiting for them. The best planet might still require sealed habitats, heavy shielding, artificial air, and carefully controlled temperatures. The destination would have been worth studying, but that does not mean it was built for human biology. For this reason, the ship itself would probably remain the safest home during the early years after arrival. Rather than immediately landing, the crew could settle into a stable orbit while robotic probes examine planets, moons, asteroids, radiation belts, and available resources. After surviving 1,000 light-years, there would be little reason to risk the mission by rushing through the final few million kilometers. Water would become one of the most valuable local resources, because it can support life, provide oxygen, contribute to shielding, and supply hydrogen for industrial uses. Carbon, nitrogen, metals, and other materials would matter as well. A visually beautiful planet with few accessible resources could be less useful than a cold moon or asteroid field rich in the materials required to keep the settlement alive. This would change the meaning of exploration. The crew would not simply ask which world is most Earth-like, but which combination of objects can support a permanent human presence. A rocky planet might provide gravity and minerals. An icy moon might provide water, and nearby asteroids could supply metals. The settlement could depend on an entire system rather than one perfect world. Any evidence of biology would complicate the decision immediately. Even simple microbial life would force the crew to think about contamination in both directions, because releasing Earth organisms into an alien environment could destroy scientific evidence or alter an ecosystem before anyone understands it. Bringing unfamiliar biology into the spacecraft could be equally dangerous. A living world might therefore become the least attractive place to settle, at least at first. Humans could observe it from orbit while building habitats elsewhere, preserving the environment until its biology is understood. The most scientifically valuable planet might be the one the crew chooses not to touch. The opposite possibility could feel quieter but just as profound. The travelers might find no life at all, only rock, ice, gas, and sunlight. After spending years crossing interstellar space, there may be no signal, no ruins, no organisms, and no evidence that anything has ever lived there. The only living things in the system could be the humans and whatever biology they brought from Earth. That would make the crew's isolation complete in a new way. Earth is too far away for practical communication. The sun is a faint point behind them, and every human voice in the system exists inside their own settlement. They have reached another region of the Milky Way without escaping the fact that human life still depends on a carefully controlled pocket of Earth-like conditions. Over time, the spacecraft itself could stop being a vehicle and become infrastructure. Tanks might be converted into storage, shielding reused in habitats, living modules connected to larger structures, and systems designed for the voyage adapted for permanent use. The machine that crossed 1,000 light-years could slowly be taken apart to build the place where the crew intends to stay. If a suitable planet exists, settling its surface would introduce another layer of uncertainty. Gravity might be lower or higher than Earth's. The atmosphere might be thin or chemically dangerous, and a comfortable temperature would not guarantee long-term biological safety. Humans evolved under one specific combination of gravity, pressure, radiation, and chemistry, and moving to another world does not erase that history. The first permanent settlement might therefore remain underground, inside sealed structures, or in orbit even when a planet looks promising from a distance. The goal would not be to prove that humans can walk outside without protection, but to create an environment where people can live for decades, and where future generations can grow without depending on supplies from Earth. That question of generations would soon become important, because the original travelers may not be the people who determine the long-term identity of the settlement. Children born in the new system could grow up under a sky they consider normal, learning about the solar system through recordings, maps, and stories. Earth could become a place of origin rather than a place they expect to see. For the original crew, the emotional relationship would be different. They would remember the real sunlight of Earth, the old constellations, familiar weather, and a planet whose current state remains hidden behind a 1,000-year delay. The destination might become home, yet memory would continue tying them to a world that no longer exists in the form they knew. There is also a possibility that would make arrival even stranger. Humanity might have continued developing after the ship departed and eventually launched faster spacecraft. A mission sent centuries later with better propulsion could cross the same distance in less Earth-frame time and reach the destination not long after the original crew, or even before it, depending on the speeds involved. The travelers could arrive expecting to be alone and instead find evidence that people from Earth had already reached the region. Their own ship might have been the most advanced machine ever built when it left. Yet after 1,000 years of Earth history, it could be technologically ancient compared with later missions. No message sent from home could reliably warn them in real time, because the information would have to chase the spacecraft across interstellar space. The crew might learn about centuries of technological progress only through delayed transmissions, or through what they physically discover when the target system finally comes into view. If no one has arrived before them, then the crew becomes the first human presence in that part of the galaxy. Their maps change from predictions into local measurements. The target star becomes an everyday object in the sky, and the settlement begins developing its own history independently of the solar system. Every discovery they make would face another 1,000-year trip before Earth could receive it. A new planet could be mapped, a settlement could be built, and generations could pass before the earliest detailed reports arrive home. The destination could develop an entire local history, while Earth still waits for confirmation that the original spacecraft survived. That information delay means the settlement and Earth can no longer function as parts of one ordinary society. They may share an origin, language, archives, and cultural memory, but decisions cannot be coordinated across a 2,000-year round-trip communication time. Each side has to live with information about the other that is permanently old. The destination, therefore, becomes more than a distant colony. It becomes a separate human present. The people there wake beneath a different star, solve local problems without help, and build around resources that do not exist in the solar system. Earth remains emotionally important, but it can no longer define daily life. Eventually, the practical questions of arrival would settle into routine. The ship would be safe, the local system would be mapped, and the crew would know whether it has found a place where humans can remain. At that point, the greatest uncertainty would no longer lie ahead of them. It would lie behind them. 1,000 light-years away, where Earth has already lived through more than a millennium that the travelers have never seen. The same relativistic physics that allowed them to reach this new system within part of a lifetime could, in principle, carry them in the opposite direction as well. But returning to the solar system would not mean returning to the life they left. Another 1,000 light-year crossing would allow another enormous span of Earth history to pass, while the travelers themselves might age by only decades more. The ship could retrace its path through space without retracing its path through time. And once the destination has become real enough to call home, the final question is no longer whether a human could travel 1,000 light-years, but whether anyone who made that journey could ever truly go back. In a purely physical sense, the answer could be yes. If the spacecraft survived the outward crossing, if its propulsion system could be restored or rebuilt, and if enough energy were available, nothing in relativity forbids the crew from turning around and traveling toward the solar system again. The return would be another 1,000 light-year journey through the same galaxy, governed by the same limits that shaped the voyage outward. But the meaning of going back changes the moment time is included. The crew may have experienced only decades during the first crossing, while Earth accumulated more than 1,000 years. A return at a similar speed would allow another enormous span of Earth history to pass. The travelers could leave home, reach another star, spend years there, and then cross the same distance again, while aging by only part of a human lifetime. Yet the solar system they return to could be separated from their departure by more than 2,000 years. That makes the return journey different from anything familiar on Earth. Coming home usually means returning to a place that has changed only a little while we were away. But a relativistic traveler could return to the same coordinates while arriving in a completely different age. The planet might still be there, the moon might still circle it, and the sun might still rise over the same oceans, while almost everything human has changed. Cities could have expanded, vanished, or been rebuilt beyond recognition. Languages might have evolved, political borders could have disappeared, and the institutions the crew remembered might survive only in archives. Every person they knew would be long gone. Even if humanity remained on Earth, the travelers could feel less like citizens coming home and more like people from ancient history suddenly appearing in the present. Technology could widen that gap even further. The ship might have represented the greatest engineering achievement of its era. Yet after 2,000 years of development, it could look primitive. The civilization waiting in the solar system might have built spacecraft that cross interstellar distances more efficiently, created habitats throughout the system, altered human biology, or developed machines that make the original vessels seem as old-fashioned as a sailing ship. There is no guarantee that history would move smoothly forward. Civilization could have collapsed and rebuilt, migrated away from Earth, changed into something smaller, or disappeared altogether. The crew would not know which possibility was waiting for them until information from the solar system began reaching the ship during the return. That process could become one of the strangest parts of the entire journey. On the outward trip, signals from Earth struggled to catch a spacecraft racing away from them. On the return, the ship is moving toward incoming light, so centuries of broadcasts and observations could be received at a very different apparent rate. The travelers might spend years watching fragments of Earth's history arrive in sequence while the solar system grows closer. Those messages would still describe the past. The crew could learn about discoveries, wars, migrations, changes in culture, or the rise and fall of entire societies while knowing that every event they are watching has already happened. The information may feel immediate inside the cabin, but it is still light that spent centuries crossing the distance. If the solar system remained highly technological, the first signs might appear long before Earth itself becomes a clear target. Artificial structures, unusual energy output, settlements around other planets, or altered patterns of light could reveal that humanity continued developing during the crew's absence. The travelers might have spent years building a fragile home around another star, only to return and discover that the solar system has become something they would once have considered impossible. Perhaps Mars is heavily populated, perhaps large habitats surround the Sun. Perhaps most humans no longer live on planetary surfaces at all. The crew could return expecting to recognize home, and instead find a civilization that considers Earth only one part of a much larger human system. There is also the possibility that later spacecraft already crossed the same route. A mission launched centuries after the original travelers left could use better propulsion, better shielding, and more efficient navigation. It might reach the destination not long after them, or even before them, depending on the speeds involved. That possibility changes the meaning of being first. The original crew may have crossed 1,000 light-years, believing they were opening a path into the galaxy. Yet by the time they arrive home, their journey could be remembered as one early attempt in a long history of interstellar travel. Their technology may be ancient, but the fact that they survived would still make the voyage important. The personal cost would remain. The travelers would be among the rare people who experienced the passage of centuries without living through those centuries in the ordinary way. They did not sleep for 1,000 years or disappear into some magical shortcut. They simply followed a path through space-time that allowed much less time to pass for them than for Earth. As the return ship begins slowing near the solar system, the sun would brighten again, and the planets would become distinct. The visual transition might feel comforting at first. The same star is ahead. The same planetary orbits are waiting, and the broad architecture of the solar system still exists. But familiarity would stop at the astronomical level. 2,000 years of human history could leave enormous changes on the planet below. Coastlines might be slightly different. Cities could be visible where none existed before, and the night side of Earth might show patterns of light unlike anything the crew remembers. If civilization survived and advanced, Earth could look more engineered from space, surrounded by orbital structures and artificial activity. If civilization declined, the planet might look strangely quiet, with fewer signals and less visible infrastructure. In either case, the surface could still appear blue and white from a distance, creating the unsettling possibility that the planet looks almost unchanged, while the human world on it has become completely different. A crew that finally enters Earth orbit might recognize continents but not countries, oceans but not coastlines, weather but not cities. The physical planet offers continuity, while history removes almost everything personal. The travelers could stand above the same world they left and still have no living connection to the society that sent them away. Landing would make that contrast even stronger. Gravity would feel familiar, the atmosphere might smell like home, and the sun would rise at the same basic pace. But the people waiting there could speak differently, dress differently, and know the travelers mainly through historical records. The crew may remember streets and neighborhoods that have not existed for centuries. This is why relativity turns a round trip into something more complicated than a journey there and back. The spacecraft can reverse its direction through space, but it cannot reverse the time accumulated by Earth. It can return to the same planet without returning to the same life. The deeper lesson is that distance and time become inseparable at relativistic speed. At lower velocities, the problem is straightforward. The journey simply takes too long for one person. At higher velocities, time dilation solves that problem for the traveler while creating a new one, because the outside universe continues aging. The 1,000 light-year distance is large enough for that trade to dominate everything. Communication becomes historical. Navigation becomes predictive. Shielding becomes essential. Energy becomes extreme. The sky changes, and the crew's personal timeline separates from Earth's. The voyage is not just a longer version of crossing the solar system. It changes the meaning of travel itself. At departure, Earth is the center of the crew's world. The sun dominates the sky. Mission control is close enough to answer, and the destination is only an old image collected through telescopes. As the ship accelerates, those relationships slowly reverse. Earth shrinks into a point, and then into delayed information. The destination becomes more immediate, while home becomes more historical. Relativistic motion distorts the sky, and time dilation allows the crew to cross a distance that would otherwise demand many generations. By arrival, the travelers are physically present in a star system whose current state no observer on Earth can yet see. If they stay, that system becomes their present, while Earth becomes their past. If they return, Earth becomes their present again. But the historical world they remember remains unreachable. There is no route that solves both problems at once. A slow journey preserves the relationship between clocks, but lasts far too long for an individual human. A relativistic journey keeps the travelers alive long enough to arrive, but carries them away from their own historical era. Faster engines do not remove the cost, they change the form of it. For a civilization willing to send people outward permanently, that may be acceptable. A traveler could cross distances that would otherwise require thousands of years, settle around another star, and live an ordinary human lifespan, while Earth moves far into the future. Interstellar travel becomes possible for individuals only when departure is treated more like migration than a temporary expedition. Future travelers might grow up understanding that from the beginning. Leaving for a star 1,000 light-years away would mean giving up not only a place, but a time. The decision would be less like boarding a long flight, and more like stepping out of history, knowing that the era of departure will continue without you. That may be the hardest part to imagine, because humans naturally think of home as a location. We picture coordinates, landscapes, houses, and familiar skies. Relativistic travel reveals that home is also a moment shared with other people. And once enough time has passed, returning to the place cannot restore that moment. The crew could bring recordings, photographs, books, languages, music, and memories across the galaxy. They could preserve a detailed piece of the civilization that launched them. But what they carry would become a historical snapshot, while the original society continues changing elsewhere. In that sense, the spacecraft itself becomes a moving archive. It carries people and machines, but also a version of Earth frozen into culture and memory at the moment of departure. When the crew arrives 1,000 light-years away, or when they return, 2,000 years later, that preserved version of home may be older than the societies around them. The stars outside remain ordinary stars. The destination may be nothing more exotic than another planetary system inside the Milky Way. The laws of physics never change. Yet the journey transforms the travelers because it separates their personal history from the history of the world they left behind. If they remain at the destination, Earth continues without them. If they turn around, they return to a future they never lived through. Either way, the 1,000 light years cannot be crossed at relativistic speed without paying for the distance in time. And that may be the most important thing that would actually happen if you traveled 1,000 light years. You might survive the distance, you might reach another star, and you might even find a way back to Earth. But the moment you leave at relativistic speed, the version of home you remember begins becoming a place you can never return to. Good night.